Something. Test, test, test. Okay, I don't know, man. So... You know what? I can just go back. It's seemingly live, so I can just go into that. The reality is... Oh, there it is. Here, if I can... It's seemingly live, so I can just go into that. Okay. And I can also make sure that I'm live. Oh no. Oh no, it's still live. Wow. That's cool. So, yeah, I just checked it. Alright, so, and I have space. I have space right here. All up and down right here on the screen. You can see that on the screen. Sorry. It's like where my hand is, or you can't see my hand. Right here where I'm holding the mouse. Or you can't see my hand. Okay, welcome to the show. Welcome to the... Okay, so... I'm going to turn this down. Welcome to the show. Perfect. It's a bit hot. So... Oh, man. Oh, God. Fuck. What just happened? Oh, jeez, man. Oh, no. The show must go on. Oh, gosh. Darn it. What happened? Okay, the show's still up, but this escape key just exploded. Oh no. Look at that. Oh well, it still works. I'm gonna put it back together. Okay, I don't know what this is gonna do by me forcing it back in. Sucks, man. And I really like this keyboard too. It came free with, I fixed it, see? And it works. Came free. I got it for free. I like to bust stuff for free. So if you give me anything for free, I'll bust it. Oh, speaking of some stuff that I got these books. We could go over these later. These supposedly are like primary source, and some of it's good. I don't think it's well. It's like my stuff where it's like, oh, I just want to present it. It's too bad I don't have all this time. And I mean, when you say it's primary sources, I mean, it should be more There should be more of those. So, we've been doing this. This was the Octonian wellness scale with quaternionics, and we're talking about. Oh, if you watch my show, that's the one on Rumble. You know what I can do? I don't want to, because this is really a format, and I just wanted to keep it like, oh yeah, this thing, and like when I would use this, because it's got to be kind of limited brief. It cost me about 10 cents to run this system, an hour. So I try to tally that up. It's a little less actually. It's probably more like 7 cents. But that's, it's probably, no, now that I think about it, it's probably about 10 cents. It's 10 cents. It's 10 cents an hour to run this system. And so I got to make sure that it's like really worth it, because like, these days I got a show over here, I got a show over there. I got 3 shows going on in this house. It's like a network. It's a studio. I got AI teaching on Rumble. My Rumble account. Go over on Rumble. On Rumble, there's Agent 77, and I'm live right now. I swear to God, I'm not an AI. I'm not AI. You're like, you have 3 shows, 2 on YouTube going simultaneously. A simulcast, but not. How do you explain yourself? I'm not AI. I'm just that efficient. I'm more efficient than most AI. Actually. Way more efficient. But that's not the point. And I was like, oh man, the antics. I really should not. It was more just like, oh, expect that kind of stuff on my shows. And that's not the show. This one is more of like an explanation. Not really. You can watch some of the other videos on this channel and the other channel. I assume this one's going to get me some views. It's not important who I am as much as what I have to tell you. And so what I'm going to do is I'm going to attempt to explain what it is I do, then what I did, and then my name at the end, because that's least important part, if you ask me. It might deter you from like, oh, because maybe you're like, oh my gosh. But really, what I'm going to do is I'm going to explain that the sphere packing problem and this formula and why it's important. And this isn't really it. This is a different video. Let's just start another page. The importance. I'm going to attempt to zoom in. It does not work. That's horrible. Okay, so like a couple buttons work, but for some reason that one doesn't. I'm wondering what that is. So anyway, I'll look into it. So yeah, I was okay. So what did I say I was going to do? Okay, let's explain the problem first. The problem I'm attempting to explain here is the sphere packing optimality problem. Here, I'm just going to add a window capture. So I added that, and what I can do, you know what I can do? I don't know how that got cut. What I'm going to do is I'm going to share this as a dedicated window. Hold on. A dedicated window. Hold on. Yeah, a dedicated window. So let me just set that up here. A dedicated. Here, let me just add that. I like to have the browser up there with stuff, and I want you guys to see, because usually the show doesn't do that. And yeah, so we're gonna have that as the thing, and so I can just do dedicated. What am I doing? Uh, let's see here. Trying to think. What was I saying? Where's a good starting point? So, yeah, let's just sphere packing problem. Ooh, yeah. So, all right. So, I'm just going to check. Assuming you can see what I see. I believe so. So, arranging spheres so they occupy the maximum possible volume without overlapping. That's important. That's basically it. That's a very good summary. I was trying to explain it. I was like, oh, you know what? That's without overlapping is very important. Occupy, and the spheres can be arranged at different scales too, and they can be there's other problems too where they can be, but I think the one they're thinking of is uniform, and there's a reason that some of these it says here the problem can be generalized to spheres of unequal sizes, higher or lower dimensions, and even non-Euclidean spaces. So that's pretty good. So in three-dimensional space, the densest arrangement fills approximately 74% of the volume, while random packing typically reaches about 64%. So anyways, there's certain dimensions that are important. Anyways, you see here, it says here error correcting codes, higher dimensional sphere packings. Alright, we're going to go over those and why some of these are important, but it remains, it says here, profound implications, both math and applied sciences. Connecting geometry, combinatorics, and information theory. So today we're going to attempt to solve all of the dimensions using some very basic mathematics. And this might be solvable. I've basically written it off as one of those things, at least right now, that we can't solve. I think we can solve it, but I don't think we as humans can solve it so easily. I think we might need AI for it. So there's dense packing arrangements, hyper dense packings. There's all sorts of arrangements, and here you go, hyper packing, and this is the one we're going to be focusing on because this it says right here, unsolved problem in math. What is the densest sphere packing in dimensions other? So I'm actually going to solve this right now. It's kind of one of these self-referential things, and it explains it. I'm gonna go to integer sequencing database. So I want to make sure everything's on. Okay, and I'm going to remove, so I'll do I'm going to do 3, 8, 24, 48, 120. Okay, and there it is. Okay. This is the one. This is the sequence here that you use to solve for all dimensions. In fact, this is them right here. This is all the dimensions. I don't even have to write it out. As you can see here, there's 3, 8, 24, 48. And it starts here at 3. So, a sphere is three-dimensional. And these are all the higher densities. So this is how to solve all for all infinite into infinity hyperdimensions for the sphere packing problem. And there they are, okay? And the formula is simple. It's this one right here. And that's it. So I'll attempt to explain this further now, because some of this isn't so straightforward, but this is where we deal with modular mathematics, like right out the gate. The first prime is 2, so when you do the formula, it's basically prime squared minus 1. That's it, and it can be explained so many times, but basically that's it, and it's all of that. So it's a modular thing, and you'll notice that with this, here I'll just go back to this, in this sequence here, everything's a multiple of 24. It's a multiple of 8. 24 has 3 in it. It's a multiple. 2 is all of these things contained. So these things are like packed. You know, you can put two 24s in here. A 24 is an 8 and a 3. Okay? And and an 8 can be broken down into 2, and you can break any of these down, any dimension down, into 1 in itself infinite amounts of times. And so when we get back to the sphere packing, it says the optimal result being known only in dimensions 1 through 3, 8, and 24. It is possible that in some dimensions the densest packing may be irregular. Some support for this conjecture comes from the fact in certain dimensions, example 10, the densest known irregular packing is denser than the dense, and so that's really more like it's more like an optical illusion at that point. Like if you study analog and digital conversions, like in machines, I did a lot of this when I was studying for some experimental stuff. And when I started doing modeling, I was asking the question, why are our computer models, what's the thing that makes them, like, wrong so much? Is it really, this thing? And there's a lot of things, there's lots of issues, but this helps us understand all of it, pretty much. So for example, if we were to interchange dimensions with bits, and you had lossless audio, it's 24 bits and 48, so 28, 48 right there. 48 kilohertz is the recording, or kilobits, or whatever sampling ratios you can come up with. But basically these numbers, they just kind of underscore the stuff. Like the TV I'm looking on right now, it's 120 frames per second or 120 hertz, interchangeable, these things, these references. Also, it's on 120 volts power, some car batteries, and electric vehicles are 24 or 48 volt battery systems. These are just really efficient when the standard is, you are the generator. You are outputting these things. And some of these I don't know so much about, but goddamn if 360 isn't one, right? If you know what I'm talking about. Alright, so anyways, and then there's certain packings within packings of these things that are uniform like that, like, hey, 24 packs into that 2 times. 24 packs into this 5 times. 24, packs into every single one of these a certain amount of times. If 24 is a bigger arrangement, you can use 24 to identify higher packings within packings. That's for modularity. You see like modular things like this. People are noticed that, hey, this sequence has a lot to do with modular arithmetic and modular everything. So this formula itself, it's deep. So this right here, has implications with imaginary numbers, like how we get the number I in itself. So like the square root, somewhere in between a square root and this actually solves problems we don't even know are problems yet. So I liked that part where I'm just like sitting here going baffled as I just keep exploring the depth of it, and it's just like, holy shit, is there an end to it? And I couldn't tell you. I couldn't tell you. I would just simply say there's an end to the depth, but it goes on forever, okay? Anyway, so that's kind of a cool thing. I like that about this. That I'm like the first guy to solve that. It says here, what's the densest packing? So, it says it's unsolved. I actually solved it. It's with that one right there. But we're going to attempt to go over this. And there's some real research I haven't really explored, and I really think it's going to be cool, and people are like, hey, cool, thanks for solving that basic ass shit. So that we can study it deeper because we're crazier than you. And it's like, great. Because I got better shit to do now. Because the thing is, I mean, that's the quick of it. That's the quickest. There's different spaces. But, you know, I solved the hyperspace. So this is a hyperdensity. This has more implications in physics and high density or high energy density physics. So extreme pressures and temperatures where energy densities exceed. So some of this stuff is like optimal for plasma physics and stuff, for the study of plasma physics. And so that's really cool. Yeah, I did that. Like I created an ideal space for study with discrete mathematics. So for modeling, that's pretty interesting stuff. Oh, national security, you don't say. Nuclear, wow. That's cool. Anyway, yeah, so I did that. Anyway, so, yeah, cool. I guess you are the head P. Thanks. Yeah. I guess so. Yeah, so there's lots of problems here, but I solved that one. So, I can hide this window and show you my skinny knees. No, I'll show you my hairy arm. No, I'll show you what it is. So this is the best way I can explain it. I don't have all my notes. I just wanted to be like, fuck you, Terry Tao, or whatever his name is. Terrence Tao. I'm Taylor Taranto, by the way, and here's my formula. So the first thing we do is I'm going to write it left to right, because it doesn't really matter if we construct it in entirely constructive language that's only additive. Because nature really is additive when you add things. So this is an additive form. And the first thing I like to do is start out with my base. Okay, so that's the base. And this one is more like I'm explaining this, and this right here is I is more like 90 degrees. We'll just see it as such. And this is 180. We'll shamboozle these to 1 over 4/4. And this one 1 over 8. And I just kind of want to this one as 1 over half. And we multiply those together. We get 1 over 8, and it's more like 1 over 8, and we're gonna just inverse it with the power of -1. Okay, so then that becomes 8. So I just want to show you some of these things where you can quickly do these things with it. just to get these things like right out of the way. So it's like, it's almost saying like e and its inverse of 8 to the power of the inverse of 8. Almost. It's like saying that. And I wanted to equate that more to like, oh, watch this when we get to 8 dimensions, because, you know, number systems, I think I have it right here. Here's our number systems. And we have the binary equivalents, where this would be like all continuous real stuff, where we can measure everything in reality. Real number system, one-dimensional. We have this in binary, so we can do this computationally. And this is complexity of 2. So it's a complex, so complex, excuse me, so this equals 2. 2 dimensions, which is our complex dimension, or complex plane, number systems. And we have 2 to the power of 2, which is our 4-dimensional quaternions, and 2 to the power of 3, and 8-dimensional octonions. Okay, so like when we look at it like that, it's pretty simple. All the number systems, these are, you can go look that up and be like, okay, yeah, I see where you're going with this. That's wonderful. So we have like all meaningful, and like in 8 dimensions, I'm gonna kind of just make this its own thing. So that's 8 dimensions. We have the E8. I don't know why I keep doing equals. We'll just say equals, and we'll just say E8. This is an entirely different thing, so don't worry about anything above here, okay? I just want you to be like, okay, we can tie this in. I'm sorry for the notations. I'm just trying to do this quick. I got like 3 shows going on, and they said, you have a time limit, buddy, before you have to jump over on the other show, and switcheroo kind of thing. And so, you know, like, I hope you're good. It's like, okay, yeah, and this is to the power of 1, okay? Now this right here actually also equals this entire thing, not just this little stuff. So like this entire thing equals minus 1, okay? E to the power of I. So think of it like that. So there's so much stuff here, and I'm just trying to, the thing was, I was like, I want to speed run and just mash up all of the number systems and physics and stuff that were like really useful, so people would just be like, okay, cool, wham, bam, thank you, ma'am, thanks for the correspondence, let's go. So I did this on Rumble, Agent 77, that account, and you can watch. It's watching you over here, and I don't know. It's not me. I mean, it is me. So, and I have all these different shows. It's a speed run. I'm going for the gold. So, anyways, you know, 8 is also equal to 2 to the power of 3. Okay, just want you to be like, okay, so that system before, right? Okay, so now we have that in binary of sorts with Taylor power series or some shit. I have no idea. I just whizzing through this. So, anyways, this equals minus 1. Okay. Now the fundamental theorem of arithmetic. Actually, I'm going to go back to the window because we might need that for a quick proof. I'm trying to work it out. Like, what's the fastest quick proof? So we got. Okay, so quick proof. What was I even talking about? E8. Oh yeah, fundamental theorem of arithmetic. Okay. All right. It states, I'm not really, you know, it's just basically this. That's that method I just showed you, where 8 is actually 2 times 2 times 2, basically. And all things are, all numbers besides 1. Right, and so this is like that fundamental theorem where it's like, okay, and because of 1 base number counting, we actually could construct primes. We can construct primes out of any, I can make a prime number out of any number system. Any number system that doesn't follow the normal stuff. I can even find primes in those things. So primes have a distinct classification within anything where you can numerate, and but typically speaking, more generally speaking, they follow this thing. But you know, there are different kinds of primes, so to speak, and it's based on the number systems and the methods of counting involved, and basically encoding. And anything can be encoded, and Yeah, anyway. So it's really interesting. And I don't want to get into all of it because it's really not. It's got great implications, but that's really not why we're here. So really, the idea here is we're just going to pick one number, okay? And really it's any number of primes, but it's got to be prime, the same prime. And for some reason, this right here can be reduced to, I'll show you that. So let me just make sure that, okay, so the reality, if I could resize this, I wish I could resize this. This is horrible. Alright, anyway, I'm just trying to scale this. They won't let me. Oh well. That's weird, man. Okay, anyways, it's not important. The idea is that we're going to construct something. Now, the other thing is, this next thing is prime number. We only need one to create one environment, okay? And this is squared. It's literally squared. So that's actually the formula. Another way of saying it is prime squared minus 1. That's much simpler. So, example, 2 squared minus 1 equals 3, and you get that list, right? And so on and so forth. So, pretty interesting because really that's it. And the implications of that are pretty huge. Pretty huge. So, you could say, well, you can't go lower than 3. And I would say, right, but that's to get, like, I just solved that problem. So eat your heart out, Terrence Tao, with your bullshit Gauss or whatever it is. DARPA formal proof software. I think it's a, I always said it like this. I was like, well, while you're doing that, you'll be proving me every step of the way into infinity forever. That's how and I'm cool with that. So the real way to do it is you take these numbers here, and you just do that, and each one of these should prove. I don't know, some of these might not. I said this before. I said, some of these, there might be reasons why some don't. Or we just might need to spec out where the sphere packing problem, and that takes a lot of computational resources. But yeah, like I said, you'll be doing that for a long time. But thankfully, I trust it. I did 48. I don't want to show you my proof for 48. But I have proven 48. I have proven 48, and I'm pretty sure I've proven 120. So dimension 48 and 120. And I'm not going to show you how yet, because that would give, I'm pretty sure that would give Terrence Tao, DARPA, and everybody else a leg up for proving these. But they get harder and harder as you go, and they require more resources. So, and my name is Taylor Taranto, TaylorTaranto, and I'm an actual political prisoner in the United States. And that's pretty cool. And they tried to kill me, and that's even awesomer. So, I mean, no one has my story. I have the greatest shows in the world. No one can beat my shows. I'm more creative than all of these people in academics and the arts and the sciences. Man, I got so many, and I got better shit to do with my time. So really, that was probably, I just wanted to prove that more than anything. So I think I did that. Trying to get in the page here. Yeah, I'm just gonna do stuff where on my channel where I'm trying to like highlight that I'm the best. So there's a live chat. But other than that, so I should probably just edit this. Yeah, I called me Terrence Tao, like as in TAU. His arch nemesis. Anyway, so yeah, I solved this problem. Okay, let me see this. And it says here, in this video I solved the sphere packing problem into infinite optimal dimensions. Example 1, 2, 3, 8, 24, 48, 120. Using Fundamental Theorem of Arithmetic represented as any prime number. Okay, got that. Squared, emblemed. So that's more like, it's my term for like conjuncting. I mean, like I'm just slamming systems together, so it's like you can just kind of create these little creative languages. So it's emblematic of complex mathematics that are contained in two-dimensional number systems. I think I said that. As indicated when added amongst natural base e to the power of the imaginary number I multiplied by pi. Exploring the functions within up to Octonions. Okay, I did that backwards. Okay, yeah, I think I did it. 37 minutes ago. All right. Yeah, I think I did it. All right. So I really wish it let me comment. I don't know. Maybe it's like, no, just interact. So I can say something like, you know, sometimes you can solve something without having to prove it. I just want to say that there are problems. There's like, well, you didn't prove it. It's like, right, but you will be, and that's the proof enough. Some problems in math, the way you construct something, and so it's like you're saying, oh, I have to find and resolve the most perfect like thing, and it's like, well, this problem, it kind of self-references things, because the idea is like we're talking about a discrete number of spaces or dimensions of space. Okay, and so that's where like, okay, any numeration, I'm gonna actually attempt to describe this better so that you can see it. So any numeration, that's what the prime is. Okay. And there's some things where it's like, look, when I said like this thing, this description, you know, I is like this description right here, where prime minus 1 times prime plus 1, when you're doing, that's a description for imaginary numbers kind of in the first place. It doesn't have to be prime numbers. It's just like n plus 1 times n minus 1. That's kind of the description where and how we get the, you know, how we can actually describe the problem of where we derive imaginaries from. So as we look here, we're base E, which is important because it's like base E explains optimal growth where there's no restrictions. So it's just up, up, and away in the most optimal sense for growth if there was no restrictions. It's kind of like what you use for like explaining some things where people get like how you can make the best, the most out of something. And then I, which helps describe how we get this description of like what would become minus 1. And this numeration of squaring, right? And it's just like, well, it's just I don't know how to describe it. I could open it up and describe it so many different ways, this formula. So for example, where it's like if 1 were a prime and we squared it, we'd get 0. And if we put 0 in where prime would be, for analysis purposes, we get minus 1. And so we get a minus 1 is where we derive this thing from in the first place. So it's based around this first construct, which equals minus 1. I should be using this as my pointer. You can't see where my mouse is. So yeah, this right here equals minus 1. And we add minus 1 to this, and we get the number of dimensions. So this gives us discrete spaces. There's a really weird video on YouTube. I'm going to attempt to highlight it. I'm going to go on YouTube, actually. I don't remember where it is, so you have to bear with me. Okay, so basically, I'm going to attempt. Alright, so without using too much of this guy's video, because it's really interesting, but it's this guy. I'm going to pull him up on the thing just to highlight him. What the fuck is this actually happening? Okay, this guy. And in this, he describes the field of prime numbers and what they would look like under a bunch of different interpretations and stuff. And he highlights how when you line up prime numbers and stuff, they look different. And how they reasonably line up and have different patterns and approaches. And I'm not really stealing any of his work. And how those things line up with optimality and field spaces. And, and this is what primes look like when you turn them into a field. Basically squaring primes when you linearize them. Which explains, like this little picture right here, I'm not taking his work. I'm actually contributing to the study of math and physics. And so, and I hope he's okay with that. And if he isn't, then he's a real shit person. If he's a person at all. So, anyways, yeah, it's like this infinite scalable field. It's a scalar field. And that's back to my thing here. I don't want to... That's what the 2 kind of represents when you're saying prime squared. It's like this field. This scalar field where complexities arise. Like, complex 2-dimensional time even follows similar types of things. So fields. And it's like, we're not measuring space so much as we're measuring fields. I really want to say that. Or environments. Because discretized space could be like 24-dimensional. Or 24-bit audio, I meant to say. Like lossless audio. But yeah, no, that's kind of, if you really want a good video, I'm just highlighting his video too, because it's such a good video for visualizing some of this stuff when we talk about like quantum fields. And so, like, because this is more like in that stuff versus like elementary relativity stuff. So if you're a physicist and you're like, well, how does this relate to relativity? Well, it's more like, how does relativity relate to this? Okay, so that's a better way of saying it, because one of these is way more accurate and would be a better approach to start for the reasons given herein. And I think that, so that's really interesting. So yeah, I mean, that's really it. So why does this not describe 2? Because 2 is not spherical. 2 is a reduction. And while it is still optimal for space and information theory and stuff like that, data sciences, etc., like those things, information architectures, so IT, technologies and systems, IS, all of those things, information, data, bandwidth, hell, even fundamental physics stuff, well, engineering more like, because it really changes the way we think about physics. And it doesn't change anything at all, which is really great because it attaches to all of this stuff. And so I feel really great to have contributed something while I was locked away as a political prisoner for something, being entrapped and stuff. So, and, it was really crazy time to be alive. So, yeah, I'm still being politically persecuted for my faith. And I solved this while I was locked up. So, you know what they say. They always try to kill the scientists first. The people that can think for themselves and help others out of epic turmoil. So, it's my honor to contribute this to humanity. Not just the humanities, but STEAM with the arts. So, science, technology, edutainment. I meant engineering and arts and mathematics. It was my honor. This is, I want to thank John Conway. Without him, we wouldn't even know most of this. Anyways, so I am Ready Player One. You'll get the reference later because people will be like, "Holy shit, that was crazy." So, what else can I explain about it? There's so much. It just keeps wrapping around in itself forever, literally, and it's got such depth that we can't explore it. Literally. It'd be easier as a field scientist, get it, to go out and take real field measurements that we know to be accurate, and then have other people come in and replicate so this doesn't disrupt science. This contributes to science. You see what I'm saying? Because you're required to go out there and learn and perform. Because the thing is, math is only really catching up with what we already know in engineering. And that's kind of more interesting. It's the people that did something that deserve more credit, because I wouldn't know what to compare to. I wouldn't know what I was looking for. It's one of those things where you had to be human to actually figure it out. So, this is one of those problems where, I can help AI and AI can help me. But AI just would rather go to war with humans. So, and that's why you can't watch this, probably. That's why it's probably going to get pushed down in the algorithms and shit. So, anyways, there's a correspondence theorem where, anyway, I'm not going to get into that. There's so much stuff here. So, I just really wanted to be okay, let's wrap it up, because we're 50 minutes in now. And, I got nothing to show for it. Other than this show. For it. And as you can see, it's very self-referential. I've been studying it for way too long. It's and that would make it almost impossible to prove. Unless you knew exactly where it started. In which case, this might coincide with the fine structure problem. In which it is said that we know that the line is there. We just don't know which way God did the creator stroked the pen from left to right or right to left. And I would say Richard Feynman was a fucking retard. We actually know. So, it's just more shit, more bullshit where people haven't caught up with, real things, so. Yeah, but when we get into these complex planes of existence and stuff, I rest assured, while there is answers, we can get into this subject matter like complex analysis, complex analytic geometry is a great topic for all of this. It's a bit heady. That's where this leads into. But the idea is, seeing is believing, and then you can measure something, and then we can relate it, and then solve things on down, reduce it to something, some real form of whatever. With complexities, it forces us to ask questions and explore very specific things, which is fine. But we have the standard model now. I'm just going to say it like that. We have the standard model now. It's just, how do we really, understand? How do we interpret it? If that subject is more interesting to you, you might want to go explore quantum Bayesianism as a topic, cubism as an approach, which mostly just says Copenhagen approach. Interpretation is likely the best, if you really want to think about it. I mean, I'm not telling you what to think. You can come up with your own. But it's really more like what's the most likely, and based on everyone else's, including our own observational experiences. So that means we have to do the experiment. There's no other way around it. There's not much left to do. We can always ask questions. We can always solve for very specific things, but there's so many reasons to do anything, literally, sometimes. But there's also reasons to not do anything, because you already know the answer, and you know how everything, you solved it. And as I have graciously given to you, you can be like, well, you can't prove it. I'm like, I don't have to. I have enough proof already out there, and I have enough proof under my belt. But I want you to go out there and try it. Come up with your own, and if it coincides with some of these things, I'll tell you what, 48's easy. 48's another easy one. I can do it with a toilet paper roll. I swear to God I did. In a jail cell, locked away after being beaten and bruised by people that didn't like me shitting on their parade. So I was persecuted by the people that actually committed the crimes. Isn't that crazy? And okay, anyway, so that's pretty cool. Anyways, that happens a lot actually in human history, where it's like, the intelligent people, like, they take a stand against tyranny and shit, and for the right things, and everyone hates them for it. And then at the end, it's like, oh fuck, we really fucked up. Yeah, no shit. So anyways, while you're, proving me right for the rest of existence, isn't that wonderful? I'm sure they have a replacement, body snatcher clone picked out for me or whatever, but in the meantime, I'll just keep winning. So that's kind of the show. I didn't mean to really go on there. If you have any comments, just feel free to add that in the window licking tiger, message retracted. Message retracted. Message retracted. Wow. Crazy, man. Crazy. Message retracted. And of course they don't have anything. Doesn't have any content. But anyways, yeah, that's interesting. Window licking tiger. Weird. With the vertical red and white stripes. I wish I was there for that. Oh man, too bad. My eyes were closed. It's one of those quantum entanglement issues. So anyways, yeah, no, it's really interesting stuff. Anyways, it's really, at this point, there's much more technique involved. I just want to get those fundamentals out, and it also helps me get, the therapy I need, since no one's really trying to help me. And everyone's out to get me and trying to ruin me. It makes sense, though, right? I mean, that I'm that good. And Taylor Taranto beat Terrence Tao to the punch. I mean, that's pretty fucking special, especially when he's locked away in jail. Me being me. And no one else. So, no, I did that. And it's much more there's depth to it, of course. You're like, oh man, tell me the story. It's like, well, I kind of did, but I don't really have much time left on this planet. Um, so I'm more like, anyway, man, only Ermina likes to send me messages and delete them. So imagine whoever this is not here for math. I don't know. But yeah, we're doing the show. Anyways, I think it was a good show. Do we have any other good stuff going on? I think I can explain more with this, but really that's it. That's the formula. Yes, you can go, and yes, you can construct things that are also squared. It can be like, so some people are like, is there a one, is there a plus, is there a power of 3 that you just add? And it's like, you can. It's literally this language, if you will, this system of constructing right here is really simple. It's more of a natural science language and stuff, but it's just adding the entire thing as if, and then like, what's the power? And it helps things kind of group or categorize based on the power. And the power has some sort of meaning. I don't really get it other than dimensionality as an approach, and so this one is like a very complete set by itself. I thought it was really unique and novel. The simpler something is, the better, and I think that that's the simplest it can get. So, and I'm not going to go through it just too much. I'm just going to say it's really unique that, you know, so this is like a transcendental, which is much more beautiful, pure math, and that it elegantly resolves into -1. So that this right here resolves into -1. Sorry, I'm doing the mouse thing again. I'll use this as my pointer. Whereas this is more a discrete space. So if you think of this as like analog or a continuous space, if it even is, that's numeric. And whereas this is more of a discrete space, it comes out really, really interesting. No matter how, the more I study it, I'm just like, maybe it's just because of the simplicity involved. You know, with the 1, 2, and 3, you get these numbers that are just so goddamn gorgeous sometimes, and it's like, how do these things? How are these things like the Platonic solids of nature, 1, 2, and 3? People always get to that point where it's like, wouldn't it just be easier to just do everything computationally and ternary for natural sciences and stuff? And it's like, yes, it would, and a bunch of other stuff too. But you know, you can also encode just about anything in binary. So, and there's integrity in having binary. So, you know, and enumerating binary into like all the way up to Octonions and stuff is kind of nice for like those things, because you know, the thing is, really higher dimensional math and stuff, it's not too hard. It's really not that hard. It's like arithmetic. It's all arithmetic. So I want people to be like, oh, well, you know, when I approach that, you know, just think of space in general. When you're thinking about higher dimensions and stuff, that's basically this problem. So the implications of it, you know, you can just go study all that. Like, oh yeah, it's error correcting codes, 24-bit error correcting codes. Think about that. Binary, octal, all this stuff. There's so many, and any variation there, and anything that uses those things, which in computer science is practically everything. So you can but the thing is, in modular forms and stuff, eventually we start getting into, well, you know, functional groups and programming. And, you know, your code is going to look a lot like You know, the leading person on this is like formalizations of algorithms, which would be like Knuth, the mathematician Knuth. He likes to just write up on everybody else's stuff. So there's Knuth. He knows quite a bit about algorithms and like formalizing those things, like search functions and stuff like that. And that's more in the in terms of the P equals NP, which is really interesting. But he keeps coming back at it. And he hasn't even, I mean, in math it's a big deal, but you want to have real physics behind it. Like, oh yeah, you see this often. In which case, just because we can program something, what is the formal definition of an algorithm? You know, like, I think we've already got that stuff. So Knuth is kind of like on his own. I'm not going to join Knuth in that endeavor. Because it's kind of like, well, maybe he's onto something, maybe I'm wrong, I don't know. I just feel like, okay, there's like a million ways to crack an egg kind of thing. There's like infinite ways to crack an egg kind of thing. So I more want to just focus on like that as the point of that, where it's like, yeah, I don't know. I don't own any of those books of that, those like encyclopedias of algorithms or whatever, which are great. I fucking think they're great. I don't want him to stop. I think they're great. I just want it more. I mean, it's more like a STEAM thing, like, than it is a STEM thing for me. But what do I know? He might be onto something. I might be. He's also of the idea. He's of the mindset, or at least increasingly becoming more and more of the mindset, that there is, you know, one kind of problem, and we just haven't defined that algorithm yet. So keep going, man. You might be onto something. I got better shit to do with my time. So I've called out two mathematicians today, Terence Tao and Knuth. I don't know. And I have established myself, at least on YouTube. I should just say some shit in the comments when this is over. Definitely the description. Window licking tiger. That's crazy, man. Yeah, I'm definitely onto something. I have these little micro tests always going on in the background. Window lickers staring at me. I bet you I know why, too. No, you know what it is. They try to drive up the paranoia, but they use all these other methods to spy on us. Especially Wi-Fi. So, keep that in mind. Wi-Fi's the devil. Alright, anyway. I can hear that I still have a little bit of time, but I really should get going back to the other shows that I got live streaming. I'm definitely not AI. So, if you're asking, like, are you AI? No. No, my tools are taken. I might look a little, usually I look like Blade Runner. Anyway, right now, I'm a time traveler. So, yeah, and just because time is complex doesn't mean that, like, it's real. Just remember that. So it's not 1D or 2D. It just represented that way in some things as we describe things. And space is required for time. Like, it's such a self-referential thing because this does explain space and time. But it does it together. And it removes time entirely. So there's still a spatial dimension. So if you add time, you can add time. In which case, to do that, it's just prime squared. So you would say, is this time? And it's like, no. But this explains the photon and relativity really well. I don't know why, but I mean, like, you can start here almost with everything. So, like, this is such a great practical method. In physics, you could say, well, you know, let's just start here when we're describing a set. So this is saying nature, and it's God as a creation. You just created nature as a model. You know, there it is. I am God. And it's really not. It's really just saying, like, okay, get ready, because really just took the square root away of -1 kind of thing. And it's not that either. It's so complex. But basically, if we were to just model like a photon, just say a photon is this, and it's traversing, it does this where it's in a line, but it does it like this. You saw that? It's like loop. So is that, well, if we were to draw it like this, a photon, if that's a particle, it's like this, and then like this, and then like this, and then like this. And if we did it again, it'd be like this, and then like this. This is the I part. So, and then it goes like this, and then like this. And what you're seeing here, maybe you're not seeing, but basically, if this thing were going along a line, you can really only see it when it's moving. So that's why I did it from here to here. But basically, you don't see that because so this is pi, okay? So this is E, which would be like C of E equals mc squared. So E equals mc squared is like a way of saying this kind of E, because we're describing a photon, the limits of matter itself. And because the photon exists, this actually describes the photon very well. It exists as a particle and a wave. So it transitions between this state of space. And so that's kind of what we're describing with this. Euler's E to the power of I times pi. It like changes, so it goes pi. It doesn't really matter which order we put pi or I in, but we'll just say pi, and then it goes into it goes into a complex plane. So it goes up, or it goes inward or outward. You can't tell. You don't know. That's what it did, and then it does it again. It creates this little hump, and then it goes away. And so it's a wave and a particle. And that describes the photon's nature, the very nature of the photon. Wave-particle duality. It just kind of interweaves back and forth. And it supposedly, still, under this, still follows the standard model, which puts a lot of some of the physics I like out of the window, where it's like faster than light models and stuff. So this follows standard models and stuff like that. And, you know, does it change? Yes, there are complex ways around light, faster than light, but I'll tell you what, it's not as linear, in which case, you know, it's possible we don't know what those things are. And odds are, because they're not linear, they're slower. Because well, that's not necessarily true. There could be higher, but it's not as likely. I'm just going to tell you right now. Just want you to know that, where it's like, okay. So this actually helps us understand general physics and advanced physics very well at the same time. So I'm not like, oh yeah, we have to erase anything. The weird part was, I was just like, hey, you know, this, in almost every single physics and math physics construction and system I know, like, this works and describes everything. So it's more like, okay, with other people's stuff and other people's science, we can go back and attempt now with all of this stuff to reinterpret it. It just helps. It doesn't hurt. It doesn't hinder. It just contributes. So that's a wonderful thing when you have something that's like, oh yeah, by the way, I did this from jail. I didn't have a lab. So this would be more like theoretical stuff that's very useful. And helps. I think the best part was education. Like, it's super useful in education more than it is in like practical senses. But that it works with every other system is really useful. So if you're like if you're a practician more than a theoretician, it's useful either way. This is like the most useful stuff, especially if you're just like this helped me understand relativity all over again in ways that I didn't think were possible, and drop a bunch of dumb shit, like a bunch of like intellectual baggage that I've collected from listening to other shitty scientists and mathematicians over the years that didn't understand things. So this was really useful stuff. And so, does it change things? Yeah, it changes things, but I think mostly in our understanding of how things work and why math is not always like is not the best tool. And I'm not like saying we should stop. I'm actually saying no, you should keep going. In fact, use this for your practice problems. Use this for understanding things in math, because I think it's easier to understand math than it is to understand physics, and there's no reason for that. Because we're doers, not really just sitting around in a classroom all day. We wouldn't understand it without word problems, in the back of the textbook. So this helps you understand word problems better if you actually think like a mathematician, which is like thinking like a physicist too, which is like thinking like an engineer, which is like thinking like a sculptor even, which is just modeling. You're just a modeler. You just model with these things. That's all it is. It's all it ever was, and it's all it mostly ever will be, unless you do something with it. So, go out and engineer something. Go tinker with some stuff. This helps you understand like the logical flow for, if you wanted to like start your own company even in essence, because you would do things so efficiently with processes if you just explore this just in general. Because remember, this works with combinatorics, which works a lot in game theory, and game theory works a lot in economics, and it's modular arithmetic, and it works with natural sciences and all sorts of stuff. So basically, you can model more accurately now with this stuff, especially if you understand it better. So there's so many things. I just want to push you to do something. Because right now I'm in the middle of running a news network that's been shut down 1,000 times, and I have AI that's just sitting there waiting for me to push a button in the background. So I just kind of want to just share that with the world and move on. So that's continuous space right here, right? That's it in 3D. And quaternionics, you can use relativity with three-dimensional space one time. So that's really nice. And then you can buy quaternionic, which is comparative sciences or analytics, or differentials and things like that. You can differential sets, equations, all sorts of stuff. Anyways, so then you have this discretized. And right now, this is probably the most pure thing you can use for analog to digital conversions. I hope that was helpful, because I got to get back to my show. So thank you for tuning in. Signing out.